this shape of our wing with ribs and a V channel for the main support. We use two different material types. We use Nylox, which is a 3D printable material, and we also use cardboard for weight savings purposes. So moving into the assumptions of the problem, we used the assumptions that everything was linear, elastic, isotropic, and homogeneous. And to idealize our geometry, we set up the problem into two different cross sections: the outer triangle, which is the side length of A, and the inner triangle, which is the side length of A sub I. A headlong view of the cross section. We have our y-axis here and our z-axis here. You can see the length of the beam, and then the cross section is shown here as well. So then we're solving for this deflection delta. Moving into finding the second moment area in terms of A and T, we have IXX. So we're subtracting the inner triangle's moment of inertia from the outer triangle's moment of inertia to give our total moment of inertia. And we're finding moment of inertia for both the outer triangle and the inner triangle using this equation here. Substituting in some terms and changing things around, we can take the area integral of y squared with respect to the area, and then giving it bounds. We're going from y1 to y2, and then plugging in values for our area gives us this equation here. Using MATLAB, we solve this equation, and then plugging in A sub I into this equation gives us this equation here for the inner triangle. And thus, the total moment of inertia is the outer triangle minus the inner triangle as shown here. Next, we're going to find the deflection in the y direction in terms of v. We're going to start with the moment, and then solving for the rate of acceleration for the deflection, we have this equation here. So we're going to move the EI over here, and we're going to integrate twice to get it in terms of v. When we're integrating, the constants C1 and C2 from a double integral are going to be equal to 0, which leaves us with this equation here in terms of L and Z. When the coordinate system is placed at L equals 0, then Z is going to equal L. Substitute this term into here to get the final equation for deflection, which is negative W L cubed over 3 EI, which can be found in the textbook. So when we plug in terms of A and T for IXX, we have this little bit daunting equation here to show the overall deflection in terms of A and T. This makes it convenient for running the simulation on multiple different geometries, so we can plug in any value for A and T and any value for EWL that we want to find overall deflection for different materials and different sizes of the geometry.
While conducting research on the most desirable airfoil shape, the team concluded that a deep camber rib would provide ample lift while not compromising on stability. It was also important that the shape could be repeatedly produced. The first attempts of this design were made using the 3D printed Nylon X. Our initial impression of the 3D printed wings was that the infill of each rib had increased the weight quite drastically. We still went ahead and attached these wings to our body and did several test flights. Although we had several stable flights, we concluded that the additional weight had produced a much too small glide to descent ratio. Additionally, we found that our manufacturing process of putting the skin over top of the wings was allowing some air to get caught actually inside of the wing. In the next iteration, we'll address the weight and the skin manufacturing process.
Alright, so our results, plugging in the values for both Nylox and cardboard. Again, Nylox is a 3D printable material and cardboard is just standard cardboard. Our moment of inertia being 6.53 times 10 to the minus 9th. And our deflection calculation comes out to 2.05 millimeters. Cardboard, conversely, is different values for A and T, and obviously different values for our elastic modulus and density, and gives us a moment of inertia of 1.5 times 10 to the minus 9th, and a deflection of 2.24 millimeters. So the team made the decision to go with cardboard despite this higher deflection. This deflection is still well within the range of the cardboard strength, and making this choice and using the calculations for density, we can show that we're having a weight savings of 3.7 grams per meter of wing that we're using. So this is important, and I think it's going to help with the flight model in the long term.
Our calculations using the cardboard material provided reassurance that they would both be structurally sound, as well as provide a fast means of producing multiple iterations, ensuring that the wings were covered with 2 layers of plastic and then heated so that they would then conform to the rib shape. We created the skin of the wings. Additional spars were added between each rib after initial tests showed that the cardboard would bend in too far after applying that skin. The final material cost of the JunkYard jet is $5.50, giving all tools such as the heat gun and box cutters are provided. The final design of using an equilateral triangle cross-section to our cardboard wing core is rated to support a maximum of 2.25 newtons, or equivalently 0.2296 kilograms. The provided test load of 0.15 kilograms has a final design factor of safety of just over 1.5. Additional citations and the reference MATLAB code will be provided at the end of this video. Thank you for your interest in the JunkYard jets.